Okay, so this is paper 4 and the sample paper for the exam 2022. So first look at the data. G value, C value, E value, U, this is atomic mass unit, mass of the proton, mass of the electron, Avogadro's constant, molar gas constant, and then Boltzmann constant, gravitational constant, permittivity of the free space, Planck constant, the Stephen Boltzmann. Look at this here. Permeability of the free space is not mentioned here. So you have to remember 4 pi into 10 power minus 7. Now, from 22 onward, it will be not the part of this list. And then this is the AS based formula. And then A2 formulas. Only these formulas will be covered. This is new for you. This one and this one. Now we start the question 1. The question is, explain how the forces on the satellite can result in the satellite being a circular orbit around the planet. So look, the force of gravitation is equal to weight plus centripetal force, but in the orbit, G is inversely proportional to D. D is too large, so G is very small, weight negligible. Thus, Fg, the gravitational force, is centripetal. I mean, the centripetal force is provided by the gravitational force between the planet and the star. This is the answer to this part. Now, move to the next one. The Earth and the Moon may be considered to be a uniform sphere that are isolated in space. The Earth has a mass m. This is Earth. And its radius is capital R and the density rho. The Moon of mass m in a circular orbit of Earth, and the radius of the orbit mean this radius r is equal to n times r. Moon makes one complete orbit of the Earth in time t. Show that the mean density rho of the Earth is given by the expression this. So look at this. Gravitational force between Earth and Moon is providing the centripetal force. So this is the formula for the gravitational force, Gmm over r square, but instead of the r, we will write nr because the radius is equal to n times r. It's given here. Look at this. And then centripetal force is mr, mean m nr omega square, small m cancelled. Then this nr multiplied over here, it becomes cube. So gm over n cube r cube is equal to omega square, and omega is 2 pi over t. So 2 pi over t whole square. Now gm over n cube r cube, 4 pi square over t square. But we have to write this mass in terms of the density and the in terms of the density and the volume. So 4 by 3 pi r cube multiplied by density, this is a mass. Now 4 cancel both sides, r cube cancelled, 1 pi cancelled. So after cancellation, it is rho is equal to 3 times pi n cube over this g and t square. So this is the answer, this one. And it's similar to this. Next, the question is, the radius of the Earth is given, and the distance between the center of the Earth and the Moon is also given. Look, the radius of the Moon is represented by nr. So n is equal to the radius divided by r. The radius of the orbit is given, radius of the Earth given. So when you will divide it, the answer is coming 60.1. So n is 60.1. Mean 60.1 times greater than the radius of the Earth. This is the orbit radius. So this is the formula we have proved. 3, pi value, n value, g value, and look, this is 27.3 days multiplied by 4 in hours, multiplied by 3600 seconds and square. You will get this answer after calculation. And next question is, a cylinder contains 5.12 moles of an ideal gas at the pressure of 5.6 and 10 power 5 Pascal and the volume 3.8 10 power minus 2. Calculate the thermodynamic temperature scale. So simple, PV is equal to nRT, T is equal to PV over nR. This pressure given, volume given, and the moles given, and R molar gas constant 8.31. So after calculation, the answer is coming 500. Next, the average kinetic energy of a molecule, single molecule, is 3 by 2 kg, where K is the Boltzmann constant, T is the temperature. Gas is heated at constant pressure so that the temperature rises by 125. Show that the new volume. Look, PV is equal to nRT, N constant, R constant, T constant. So V directly proportional to T. So we can write V1 over T1, V2 over T2. Initial volume this. Initial temperature is calculated here 500. Second volume required. And the second temperature, this is the increase, mean 500 plus 125, 625. And after calculation, this is proved. Next, calculate the increase in internal energy. Increase in internal energy of the ideal gas exactly equal to the increase in kinetic energy, and one molecule kinetic energy increases 3 by 2 K delta T due to the increase, and multiply by N, this becomes total 3 by 2 Boltzmann constant, change of temperature 125, and the number of the particles. Number of the particles are calculated by the number of moles and multiply by Avogadro's constant. Number of moles, Avogadro's constant. So answer is this 7980. This is the increase in internal energy. Next, use the information to calculate the external work done during expansion. Mean the work done by the gas. And the work is pressure multiplied by change of volume, pressure constant, volume changing. So final volume minus initial volume. Answer is this. And this is work done by the gas, so minus. Next, use the first law of thermodynamics to determine the total thermal energy transferred to the gas, and B, explain your reasoning. Look, according to first law of thermodynamics, Q is equal to U plus minus W, mean heat supplied, increase in internal energy, work done by the gas. So you have calculated here, which is 7980, and the work is also calculated, this minus W here by 3. So the total heat supplied is 13300, 13,300. And the next, a bar magnet of the mass 250 gram. Remember, this mass is suspended from the free end of the spring as illustrated. The magnet hangs so that one pole is near the center of the coil of the wire. The coil is connected in series with a resistor and a switch. The switch is open. The magnet is displaced vertically and then allowed to oscillate. At time 0, the magnet is oscillating freely. At time 6, the switch in the circuit is closed, so the damping starts. Look at this. And the question is, for the oscillation of the magnet, determine to two significant figure the frequency. Frequency is 1 over time period, and the time period from this is calculated. Look, this is 2.4. So the frequency is equal to 1 divided by 2.4, answer 0.42. And then the energy, total energy of the oscillation from 0 to 6. So 0 to 6, the amplitude is constant, 1 by 2 m x naught square omega square, 1 by 2, the mass 250 gram, mean 0.250, and x naught is the amplitude, it's 1.5 centimeter from the graph. Look at the graph. Initially, it is 1.5, but we have to convert this in meter, 10 power minus 2 and square, and omega is 2 pi f, so 2 pi and f square. After calculation, this will be your answer, 1.96 into 10 power minus 4. Next, when switch is closed, the oscillations are damped. Explain with reference to the figure 3.2 whether this damping is light, critical, or heavy. It's light because the amplitude of the system is gradually decreasing after 6 seconds and the several oscillations are completed. So this is light damped system. Next, state Coulomb's law. Electrostatic force is directly proportional to the product of 2 point masses and inversely proportional to the square of the distance between them from their centers. Then, two charged metal spheres A and B are situated in the vacuum. The shortest distance between the surface of the sphere is 6. The movable point P lies along the line joining the center of the two spheres, a distance x. The variation with the distance x of the electric field E, mean electric field strength, is this. Look at the graph. One side is positive, other side negative, and here it is 0. The resultant electric field is 0. So look, if this is positive sphere. When electric field is drawn, so this is a neutral point. Mean here, the electric field is 0. Now the question is, use the figure to explain whether the two spheres have the charges of the same or opposite sign. Electric field strength is a vector. In graph, there is a 0 resultant electric field. Thus, both are similarly charged, because when they will be similarly charged, then definitely there will be no field, neutral point. So either both are positive or both are negative. Next, a proton is at point P, where x is 5 centimeter. Use the data to determine the magnitude of the acceleration of the proton. Acceleration is force divided by mass, and F is equal to EQ. E is the electric field strength, Q is the charge of the proton, M is the mass. So first we will look at the graph for electric field at 5 centimeter. So at 5 centimeter, it is minus 3 into 10 power plus 3. So 3 into 10 power 3, charge of the proton is 1.6 10 power minus 19. Mass of the proton will be given 1.67 in 10 power minus 27. It's given in the data. So the answer is coming 2.9 in 10 power 11. Next, the electric potential gradient is related to electric field. Yes, electric field strength is the electric potential gradient. Electric field strength is the negative potential gradient of potential distance graph. So the answer is potential gradient is electric field strength. Thus, electric field strength is maximum at, look. So electric field strength is maximum here, which is 6. So when electric field strength is maximum, mean the potential gradient is maximum at 6. So first we have to inform both are equal, and then we have to find the value, maximum value from the graph. And the next is a sinusoidal alternating potential difference from the supply is rectified using a single diode. The variation with time t of the rectified potential V is shown. This is the graph. Determine the RMS value of the supply potential difference. VRMS is V naught divided by under root 2. So the peak value is 8. So 8 divided by under root 2, answer is 5.7. State the type of the rectification. So half of the wave is missing. So this is half wave rectification. And then this is the circuit. Alternating potential difference is rectified and smoothing using the circuit. The capacitor has capacitance 85 microfarad and the resistor has a resistance R. The effect of the capacitor and the resistor is to produce a smooth output potential difference. The difference between the maximum minimum is 2 volt. Means when these two are in operation, the smoothing occurs and the potential drops only 2, mean 8 to 6. Draw a line to show V out between 1 and 5. Look at the graph. One is this. So the capacitor discharges. This is the curve. And the maximum value, the minimum value is 6. This is the difference because it produces only 2 volt difference. So 8 minus 2, 6. So this is the lowest level. So from 8 to 6, you have to draw a line. And this is showing the discharging of the capacitor. This one. And it's not a straight line. It must be a curve. Next. Determine the time in second for which the capacitor is discharging from 1 to 5. 1 to 5 answer is coming 4. But look at the graph. It discharges only from 1 to 4.5, not till 5. Because after 4.5, capacitor starts its charging. So discharging up to this point. So 1 to 4.5, the gap is 3.5. So we will write the answer here. 3.5 millisecond or 3.5, 10 power minus 3. Then use the answer in B1 and B2 to calculate the resistance. Looks the voltage is dropping exponentially. So we will write the exponential graph equation. V over V naught is equal to E power minus T over RC. This is the discharging equation. V over V naught is equal to E power minus T over RC. So V naught is the original actual voltage. V is after discharge. R is resistance, C capacitance, and T time taken for this discharge. So 6 divided by 8, E power, time taken is 3.5 into 10 power minus 3, resistance required, and this is 85 micro. So 85 into 10 power minus 6. So when it is simplified, the answer is coming 143, which can be written as 140 into significant figure. Next. A thin slice of the conducting material has its phase PQRS and BWXY normal to the uniform magnetic field of the flux density B as shown. The magnetic field is downward, electron traveling from right to left. When question is electron enter the slice at the right angle phase SRXY, a potential difference, the Hall's voltage is produced between the two phases. Use the letter. Definitely the electron, according to the Fleming left-hand rule, is deflected in this direction. Fleming left-hand rule. So this side becomes negative and this side becomes positive. So these two phases will introduce the voltage. So we will write PSVY and the other QRXW. State and explain which of the two phases name is more positive. So definitely this one, because the electron is deflecting towards this. This becomes negative. This is positive. So the positive is always at the higher potential. So PSVY, this phase is more potential, more positive. Then the Hall's voltage is given by the expression BH is equal to BI over NTQ. use the letter to identify the distance t. T is actually the thickness of the crystal, thickness of the slice. And this is Sy. Look, this is positive, this is negative. For the electric field, this SR is the distance. And this T is the thickness, this one of the slice. So you can write Sy, you can write PV, QW, RX. So this vertical height is the thickness. So Sy. Next, negative charge carrier electron are replaced by the positive charge carrier moving in the same direction towards the slice. State and explain the effect, if any, on this change on the polarity of the Hall's voltage. Look, electron is deflected in this direction, so this becomes negative. When the positive particle, suppose alpha particle, is traveling in this direction, it will be deflected in this direction, so it becomes positive. So deflection will be opposite, but no effect on the polarity. This remains negative, this remains positive. So we will write here, no change in the polarity because negative and positive charges deflect in the opposite direction. And the next is define magnetic flux, not the magnetic flux density. So we will write here, it is the product of magnetic flux density B and the area. And then we will mention the plane of the area is perpendicular to the magnetic field line. So the answer is the product of magnetic flux density B and the area, where the plane of the area is perpendicular to magnetic field lines. And the formula is phi is equal to BA sine theta. So you have to explain this. Okay. And the next is state Faraday's law of electromagnetic induction. Induced EMF is directly proportional to rate of change of magnetic flux linkage, mean E is equal to minus N d phi over dt. Next, a solenoid has a coil C of the wire bound tightly about its center. The coil has 96 turns. Uniform magnetic flux density in Weber is this, 6.8 times 10 power minus 6 into the current. Write the current in ampere. Calculate the average electromotive force. So first calculate the flux, 6.8 10 power 5 multiplied by 3.5. So this is the flux in the Weber. And then E is equal to N d phi over dt, N96, phi changing this, and the time taken this, answer is 0.95, but look at this, 3.5 ampere is reversed. This direction, 1 and 2. That's why we have to multiply this answer by 2. So the total voltage induced will be 1.9 because it is cutting twice. One forward direction, other backward direction. The DC supply is now replaced with a sinusoidal alternating supply. Describe qualitatively the EMF that is now induced in the coil C. We have to inform about the quality, not the quantity. So in alternating induced EMF, frequency of the induced current exactly equal to the frequency of the supplied current, or frequency of the induced voltage equal to the frequency of the supplied voltage. And the second, induced and supplied voltage both are out of phase, or you can write they are at the phase difference of 90 degrees. Or you can write both are not in phase because their difference is 90 degrees. Next, describe two phenomena associated with the photoelectric effect that can be explained using a wave theory. So which cannot be explained with theory. It means we have to write here the evidences for the particulate nature. So number one is there is a threshold frequency of the photon below which no electron is emitted from the metal. And the second, energy of emitted electron does depend on the frequency of the incident photon. Energy of the emitted electron depends on the frequency of the incident photon. So these are the two evidences for the particulate nature. So they are not explaining the wave nature. And the next is the maximum energy Emax of the electron emitted from the metal surface when illuminated by the light of the wavelength lambda is given by expression. Look, this equation can be written as E is equal to hc 1 over lambda minus hc over lambda naught. So when the graph is plotted between 1 over lambda and E, the hc will be the gradient and this will be the y-intercept. And this equation is derived from the quantum physics equation HF is equal to 5 plus kinetic energy of the electron. Identify the symbol lambda. So this is threshold wavelength. So here is the graph. At the x-axis 1 by lambda, at the y-axis energy of the ejected electron. And the question is determine the maximum, the magnitude of the lambda naught. So the threshold wavelength is possible when the energy of the ejected electron is 0. So at 0 energy, what is the wavelength? So look, when this line is extra plotted, 1 over lambda, this one is 2.2 10 power 6. This is 1 over lambda. So 1 over lambda naught is 2.2 into 10 power 6. The lambda will be reciprocal of this. It's coming 4.5 10 power minus 7. And then use the gradient to determine the value of the Planck constant. Gradient is hc. So we will take 2 points, for example, this first point, this second point, and then calculate the gradient. Look at the gradient here. So this gradient answer is coming 2 into 10 power minus 25. So 2 into 10 power minus 25 gradient, Planck constant required, speed of light. So this gradient, speed of light divided, the answer is coming 6.7, 10 power minus 34. This is the Planck constant. Next, the metal surface is big, in B becomes oxidized. Photoelectric emission is still observed, but the work function energy is increased definitely. When the work function energy increases due to the rust on the metal, means it's difficult to eject electron, then the electron after emission will be carrying less energy, so energy decreases. So when energy decreases, question is draw a line to show this variation. So when energy decreases, we have to draw the parallel line, but with less energy. So below the first line, we have to draw another line. So this one. And the next is data for a nucleus and some particle are given. Look, this is the data. One nuclear reaction that can take place, and the nuclear reaction may be represented in part by the equation shown. Complete the equation. So 92 charges mean proton numbers. Here 42, here 57. So these two are 7 more than this. It means 7 negative charges. Now 42 plus 57 minus 7 becomes 92. And similarly here, 235 plus 1, it becomes 236. This plus this plus this, and this is 2. So it is also. So you have to count the number of the protons and number of neutron plus protons, mass number and the proton number. You have to justify. So 7 electrons are emitted. This is the completion of the equation. Now show that the energy equivalent to the 1U is 934 1 U mass is equal to 1.66 into 10 power minus 27. Energy is equal to mc square. C is speed of light square. So this is coming in joule. Now convert it into megajoule. So this value 1.49 10 power minus 10 divided by 1 mega electron volt is 1.6 into 10 power minus 13. So you will get this answer, which is approximately 934, close to this. And the next, calculate the binding energy per nucleon of the lanthanum, 139. Now the total binding energy, look at this. This lanthanum has 57 proton. So 57 multiplied by proton mass, this one. Then it has 139 minus 57, 82 neutron, and neutron mass is given here. So this is the total mass. So the sum of the protons and neutrons, this is the mass. But when all these particles, proton, neutrons, are combined, the total mass of the nucleus becomes this. So we will calculate the difference of these two, because that is converted into energy. Now calculate the difference of these two. It is coming 1.16776 U. Now 1 U is giving you 934 mega. We have proved here. So we have 1.17. So this is the total energy released, total binding energy of this nucleus. But the question is binding energy per nucleon. And how many nucleons are there? They are 139. So what is the share of the each? So total binding energy 1.09 10 power 3 divided by 139. It is 7.84. The next, state and explain whether the binding energy per nucleon is greater, equal, or less than the binding energy per nucleon lithium. Uranium and lithium comparison. Uranium is unstable due to reaction. The products are more stable than the reactant. Thus, the binding energy per nucleon of the uranium is smaller than the lithium, because uranium is unstable and the lithium is stable. So products are always stable than the reactants. Now the next, state what is meant by the contrast in an X-ray image, degree of blackening the photographic film to compare the density of the medium in the cell. And then look at this, a parallel beam of the X-ray radiation incident separately on the sample of the bone. And question is intensity of radiation transmitted divided by intensity of radiation transmitted through the muscle. So the transmitted intensity IT over I naught is equal to e power minus mu x. So this is e power minus mu x for the bone, e power minus mu x for the muscle. Bone and muscle data is here. So e power minus 2.9 into 1.5, e power 0.95 minus into 4. When you will calculate it, this is 0.58. So this is for the bone, this is for the muscle. So this is data for bone, this is for the muscle. And the next is explain how ultrasound pulses are used to obtain diagnostic information about the internal body structure. Transmitted pulses are reflected from the organ and they are received back for processing. Intensity comparison informs about the density and thickness, and the time delay informs about the depth of the organ. Define specific acoustic impedance, product of density of the medium and speed of sound in that medium is called acoustic impedance. Z is equal to rho V. Two medium have the specific acoustic impedances Z1 and Z2. State the approximate value of the intensity reflection coefficient on the boundary between the two media. Z1 almost equal to Z2. No difference, no reflection, answer 0. Z1 is very different. So large reflection, approximately answer 100% 1. And the next, positron emission tomography make a use of the tracer containing a radioactive material that decays by the positron emission. State what is meant by tracer. Any substance injected to the human body, absorbed by the cell or the tissue, and emit radiation during decay. This is called tracer. State the name of the particles that are emitted from the body and detected by the detector during PET scanning. They are gamma rays photons. Explain how the particles in A2 are created from the positron. Emitted positron interacts with the anti-particle electron during annihilation process. Whole of their mass is converted into gamma rays photons with equal but opposite momentum. P is equal to E by C. And the next, positron can be artificially created by the process in the lab. That is the reverse of the process. This process creates both the positron and electron moving at the same speed in the opposite direction. Suggest why two particles are needed to create one positron. Initially, momentum is zero. For the zero final momentum, both particles must be in the opposite direction. Okay, so this last part. Positrons can be artificially created by the process in a lab. That is the reverse process. This process creates both positron and electron moving at the same speed in the opposite direction. Because positron and electron are interacting at zero initial momentum. So according to the law of conservation of momentum, the final momentum must be zero. So both must be traveling with the same momentum in the opposite direction. And the last question is, a star has a luminosity that is known to be 4.8 10 power 29. A scientist observing this star finds that the radiant flux intensity of the light received at the Earth from the star is 2.6 nanowatt per meter square. Name the term used to describe an astronomical object that has known luminosity. Standard candle is the answer. Determine the distance of the star from the Earth. This radiant flux F is equal to luminosity L divided by 4 pi d square. This flux intensity radiant given 2.6 10 power 9. And then this luminosity given 4.8 10 power 29, 10 power minus 9 because this is 2.6 nano, and divide by 4 pi d square. So after calculation, you can calculate the d, which is 3.8 into 10 power 80. The sun has a surface temperature of 5800 Kelvin, a wavelength lambda max of the light for which the maximum rate of the emission occurs from the sun is 500 nanometer. The scientists observing the star in A find that the wavelength for which the maximum rate of the emission occur from the star is 430. Show that the surface temperature is approximately 6700. Look, according to the formula, lambda max is inversely proportional to temperature. Mean lambda 1 T1 is equal to lambda 2 T2. Lambda 1 500, temperature 1 is 5800, lambda 2 is given 430, temperature second required, so it's approximately 6744, so close to 6700. Next, use the information in A and B to determine the radius. This Stefan-Boltzmann equation. L is equal to 4 pi sigma r square t power 4. So luminosity was given 4.8 10 power 29, 4 pi value, and this Stefan-Boltzmann constant is given in the data 5.67 10 power minus 8. Radius is required, and the temperature is given is calculated 6744 power 4, and after calculation This radius is coming 1.8 into 10 power 10. So this is the paper.